When you stand on a beach and smell the salty sea breeze, you are actually detecting a molecule called dimethyl sulfide, or DMS. On Earth, this gas is an indicator that life is present and active. It has no geological source. Instead, it's released as a metabolic waste product by trillions of microscopic marine phytoplankton and algae floating in our oceans. In late 2023, the James Webb Space Telescope turned its instruments toward K2-18b, a world 124 light-years away, and captured the spectral lines of DMS. Detecting a molecule tied exclusively to marine life on a distant exoplanet is a massive development, but it also triggers a rigorous scientific interrogation. Because our instruments are pushed to their limits at this distance, we have to determine if the signal is a genuine biological discovery or a trick of planetary physics. Caution is necessary because K2-18b has misled us before. Years ago, lower-resolution data from the Hubble Space Telescope suggested water vapor in the atmosphere. However, Webb's higher resolution revealed that this water was actually a massive abundance of methane gas that Hubble simply couldn't distinguish. Webb found high concentrations of methane and carbon dioxide, paired with a complete absence of ammonia. Because ammonia is highly soluble, a global liquid ocean would physically pull the ammonia out of the sky, leaving the atmosphere completely stripped of nitrogen-based gases. This specific chemical ratio fits the current model for a global liquid ocean. But while the math suggests the water is there, the physical conditions on the ground might make it a very difficult place to survive. The first obstacle is statistical. The current detection of DMS sits at a 3 sigma level, meaning there is still a 1 in 300 chance that the signal is just random electronic noise generated by the telescope spectrometers. In physics, a discovery isn't official until it reaches 5 sigma, where the probability of a fluke drops to less than 1 in 3.5 million. Until we gather more data, the strongest hint of alien life remains a statistical maybe. The environment itself is also a nightmare. K2-18b orbits a red dwarf star that frequently erupts with superflares, drenching the atmosphere in lethal radiation that would challenge the survival of any phytoplankton floating near the surface. Deeper down, the pressure of the massive hydrogen envelope is so intense that the water doesn't behave like a normal ocean. It is likely a hot, supercritical fluid, a state of matter that could dissolve the very organic compounds life is built from. These extreme variables make biological life unlikely by Earth standards, forcing researchers to look for ways the planet could be manufacturing these gases non-biologically. If the DMS is biological, the math requires an impossible density. K2-18b's ocean then need to be a hyper-dense soup of organisms outproducing Earth's entire marine ecosystem by several orders of magnitude to create the signal Webb detected. Skeptics point toward a geological alternative, photochemical synthesis. This is a process where the planet manufactures biological molecules using high-energy reactions instead of cells. In this scenario, volcanic sulfur from the ocean floor mixes with methane in the atmosphere. When blasted by the ultraviolet rays of the star, they undergo a high-pressure reaction that creates DMS abiotically. This suggests that K2-18b could be a planet-sized chemical refinery, mimicking the waste products of life through pure, violent geology. Currently, the data remains ambiguous because K2-18b is wrapped in a thick, high-altitude hydrocarbon haze. This haze acts like cosmic smog, scattering light and blurring the chemical lines we are trying to read. To settle the debate, astronomers are now using Webb's mid-infrared instrument, or MIRI. MIRI operates at longer wavelengths that can slice through the smog to target the 10-micron absorption bands of carbon and sulfur. This will provide the first clear look at the lower atmosphere. MIRI's data will determine if the DMS is real or a fluke of spectral noise, providing a definitive answer on whether K2-18b is an active living world or a unique chemical laboratory. Do you think we'll find these?